We were established in 2003 to facilitate sharing of data, biospecimens, and other resources, making them available to the broader scientific and research community. The repository supports the receipt and distribution of data and specimens in a way that is ethical, equitable, and efficient, allowing investigators that were not part of the original project to test hypotheses without the need to collect any new resources. We continuously promote the FAIR and trust principles, and we are among a few of the NIH-controlled access repositories honored to hold the esteemed Core Trust Seal certification. We also are members of the World Data Systems Network, emphasizing our commitment to best practices and ensuring their principles. We currently hold over 8,000 clinical data sets from 189 clinical studies, with 15.8 million images and over 16 million biospecimens, with over 60% of those currently available to the external research community by request. Our researchers are steadily increasing, having over 6,800 researchers and more than 800 public releases. Next slide. The repository is part of a broader data sharing ecosystem and plays a key role in NIH's fairness and trustworthiness goals. The NIDDK Central Repository houses a broad range of data types for secondary research and provides access to biospecimens and direct linkage to resources held outside of the Central Repository, which helps support researchers achieving multimodal research aims. Next slide. Yes. We are continuously improving and modernizing our repository infrastructure by enhancing our services and features. We will be deploying in the coming months our cloud-based analytics environment. This will allow clinical researchers and data scientists access to a suite of integrated analytic tools and cloud computing resources. This will allow them to participate in and conduct data challenges, driving AI innovation. The workbench will also streamline the data science lifecycle and facilitate discovery of data-driven biomedical insights. We envision the platform will promote collaboration, improve user experience, minimize data movement, and most importantly, advance NIH and NIDDK's research missions. Next slide. The Data-Centric Challenge series was launched in 2023. The goal is to develop tools, approaches, models, and/or methods to increase data interoperability and usability for artificial intelligence and machine learning applications. We designed this series to build on one another, with each challenge and participant tasked with developing innovative approaches for augmenting and enhancing existing repository data, improving their usefulness for future secondary research, including data-driven discovery by AI ML researchers. Please visit our website for information on past and upcoming data challenges and join the data-centric movement. Next slide. This is our second installment in our webinar series, which aims to accelerate data science and AI-driven biomedical research by fostering collaboration between biomedical researchers and experts in the field. And these webinars will also prepare potential participants for future data challenges. Our webinars are held monthly on the last Thursday of each month, and today's topic is Artificial Intelligence Fundamentals, followed by next month's Artificial Intelligence Fundamentals Applications discussion. So please register for all of our upcoming webinars listed here, and to get more information about this series or past webinars, please again visit our website. So now I'm going to kick off today's webinar by introducing our expert. Next slide. Okay. Dr. Gordon Aiello is the lead scientist at Booz Allen Hamilton with a PhD in applied mathematical and computational sciences. He works full-time developing and delivering specialized data science, artificial intelligence, machine learning, and Python trainings for clients in the Navy and intelligence community. Prior to joining Booz Allen Hamilton, Dr. Aiello worked in the Office of Macroeconomic Affairs at the U.S. Department of State, using machine learning techniques to analyze developing and emerging market economies. Additionally, he has taught courses on data science and the R programming language for the Foundation for Advanced Education in the Sciences at NIH. He is passionate about working with others to expand their understanding of data science techniques and their applications. I'd also like to mention that during last month's webinar series discussing data science fundamentals, he gave an excellent presentation, and we're glad to have him back. So without further ado, I welcome Dr. Aiello, and I turn it over to you. Thank you.
Wonderful. Thank you, Ms. Cooper. It's so great to be back with the NIDDK crew here. Thank you so much for that warm introduction. If you joined us for our Data Science Fundamentals course a couple weeks ago, you'll know that I was joined by my co-instructor, Ms. Erica Christensen. Unfortunately, she's not able to join us today, but she will be back for part 2. So I'm kind of soloing it today. I'm going to do my best to keep an eye on the chat as we roll along here. But just know that we will have time definitely at the end for questions, and we might have some time to squeeze in a short 5-minute break in the middle here. We'll see how things are kind of playing out for questions there too. But again, I'll do my best. And I don't know if you can tell, my voice is a little hoarse too, so I'm dealing with a little bit of a cold, but we'll power through here. So I'm going to go ahead and share my screen, and just if we could get a confirmation from you, Ms. Cooper or Ms. Joplin, that my screen is showing.
I can see it.
Wonderful. Okay, great. Thank you so much. Okay, so welcome. This is going to be part 1 of our AI Fundamentals series. So just to level set a little bit here, our goal is not to make anybody an expert in artificial intelligence if you're not one already. This is definitely sort of a lifelong pursuit. Things are always changing, very quickly. The technology is evolving very rapidly. The documentation and regulations around artificial intelligence are coming and going quite regularly, as well as the different types of data sets that you're working with. So this is an ever evolving field. Please, if you're feeling like, my head's spinning a little bit by the end of this, that's what we're here for. That's why we do these live trainings. So please do ask your questions, but just, not being an expert by the end of an hour-and-a-half session isn't necessarily a bad thing. We just want to give you an overview of some of the core concepts that you can use as a foundation to build the rest of your learning on and the rest of your practice on. As I mentioned, this is our AI Fundamentals course presented by Booz Allen Hamilton. Some training guidance for us here. So we're going to avoid CUI, PII, and PHI conversations. Everything is being done at the unclassified, publicly accessible level here. If you're working with sensitive information and things like that, this is unfortunately not the forum that will be able to discuss that type of work in. But more than happy to answer general questions and things like that about potential AI machine learning use cases. We highly encourage you to interact with us using the chat feature. Again, I'm flying solo today, so I'll do my best to keep up with the chat and answer your questions as they come in. But I might have to politely, push the questions to either a short break in the middle of the session today, or to our dedicated time at the end of the class today to get to those questions. It would be highly preferred that you do stay on mute unless we are on a break or at the end of the session. I know it's a lot of questions will come up, and again, this is the great thing about doing live trainings is that we can interact one-on-one with one another. We do have a large number of participants on the call today, so just in terms of easing the facilitation, we would kindly request that you stay on mute unless we're at one of those break times or if we're at the end of the session. Okay, so we went through the instructor introductions today already. That was very kind, so thank you very much. I do need to make a very quick plug for one of my primary clients here. So Erica and I primarily support something called the NAVWAR Data Science Learning Program. This is essentially a data science training program offered through the Navy based in San Diego. And a lot of the materials that we are using were pulled from content that we designed for that program. As you can see, we have courses ranging from data science fundamentals all the way up through things like data science for managers, artificial intelligence fundamentals, which we're of course taking today, as well as training on things like Python, data visualization, and natural language processing using the Python programming language. So our agenda for today, we've got a lot. There's only 4 numbers there. It seems like there's not a lot to cover, but I promise you it's chock full of great content here. So first, we're going to try and demystify what artificial intelligence is. Erica and I really do like thinking through analogy. We really like trying to simplify concepts for people as much as we can. A lot of what we're going to talk about is going to be at a very conceptual level. There are always going to be exceptions to the rules and things like that. So if you have some experience playing around with, say, something like a large language model, like a ChatGPT or a Microsoft Copilot or something like that. Again, there are always going to be small exceptions to different rules. There's always things that are changing, but we're trying to provide you with general concepts that extend pretty well to most different types of artificial intelligence. And that's worth noting here as well. Okay, first and foremost, there's not just one single type of artificial intelligence. Depending on the application you have in mind, there are going to be different artificial intelligences that are suited for that purpose. So when we're demystifying artificial intelligence and we're talking about it at a very, very high level, again, we're trying to make it as cross-cutting as possible, but just know each domain and each application is going to have its own specific nuances that, again, some of the things that we provide you, right, there might be some little nuances that you'll have to adjust for. But overall, what we're doing here is to try and provide you that framework, that overarching concept that's going to apply to the majority of artificial intelligence and machine learning systems out there. Next, we'll have a discussion on responsible AI. I know it's always fun. We want to see the demonstrations. We want to see the hands-on stuff, but is exceptionally, extremely important, especially in today's day and age with the types of data that we're working with and the types of the capabilities that these AI systems have, to have a discussion on what it means to use artificial intelligence responsibly. We'll look at some documentation at a very, very high level that the NIH has put out regarding guidance on responsible AI. This is kind of like eating your vegetables. I'm a vegetable guy, so I kind of do enjoy this stuff. And it is quite fascinating to think about what goes into the different components that have to be thought of when it comes to responsible AI use in terms of data privacy, data security, mitigating bias in data, legal and ethical considerations, copyright law, right? I'm not a lawyer, but some of these things are actually quite fascinating to think about. We'll talk about AI operations, sort of what goes into building out an AI team as well as an AI workflow. And then we'll talk about AI implementations, and we'll do some demonstrations when it comes to the AI implementation section here. All right, so we'll start with demystifying artificial intelligence. So if you joined us for our data science fundamentals training about a month ago, this sort of working person's definition won't be new to you. If this is the first time you've joined us, that's totally fine. We like to think about data science as the goal of data science is to extract meaningful insights from data. That's what we're trying to do, right? And to extract meaningful insights from data, we use artificial intelligence to help us support that mission. Okay, so that's the intersection between data science and artificial intelligence. And we're going to see a diagram, sort of one of those nesting doll diagrams in just a moment, but that's the idea. We want to extract meaningful insights from data using artificial intelligence. So what is data science? What does data science rely on? Of course, well, data, right? We need to have some type of data that our machine or system is going to learn from, all right? And at a very high level, we're going to see this on a subsequent slide, but you can think of artificial intelligence as a pattern recognition tool. That's at a very, very high level what artificial intelligence is doing. So I'm sure all seen a movie or a TV show where you've got the investigator trying to solve a crime, right? And they've got the cork board and they've got the suspects and they've got the evidence and there's just kind of red string going everywhere, right? That's sort of what artificial intelligence is like. It is looking at the data that is presented to it. It can only look at the data that's presented to it. So if there's missing data, if there's bias in your data, right? Anything that might represent dirty or unclean data, right? The system isn't going to be good enough to pick up on any deficiencies that are in the data. All it's going to do is look for patterns given what it's shown. Okay, so data is the lifeblood of these systems, and data comes in a variety of formats, including both qualitative and quantitative. So qualitative might be something like natural text, right? So something like I'm cold, I'm not very cold, that we could use like to say analyze the sentiment of something like that. Maybe negative would be I'm cold, positive would be I'm not very cold, or the temperature is fine, right? So that's what we mean when we say qualitative data, basically non-numeric information. And then the most natural form of data I think most people are familiar with would be numeric information, right? So we could talk about somebody's age, somebody's height, somebody's blood pressure measurements. Things like that are typical numeric quantities that we might use an artificial intelligence system to pick up patterns with. Right? Image data is also very popular. So image data could be something like an X-ray image. It could be the image of someone's eye, looking at capillary size and blood vessel size, things like that. right? And AI has also been trained to look at images and detect patterns and that type of data as well. If you were in our data science fundamentals training, one of the last slides that we covered was actually showing how artificial intelligence models were actually trained to pick up on, blood vessel size in the eye as a sort of proxy for renal function, right? And so these are all the types of things that AI can be applied to. It's not just numbers. It could be text, it could be images, things like that. Okay, so we're combining the idea of data with science. And by science, of course, we mean a systematic approach to trying to build out knowledge, where we have some hypothesis, and to assess the validity of that hypothesis, we have to test that against the data that's available to us. So again, that speaks to the importance of data quality, which we'll discuss in a little more detail when we get to responsible AI use. So data science in and of itself is a very interdisciplinary field. And therefore, artificial intelligence is a interdisciplinary field as well, because artificial intelligence, as we'll see, is a subset of data science. The main components that go into data science and artificial intelligence are things like computer science and programming. So we need people that know how to manage data. We need people who know how to code. We need people that know how to stand up large scale IT infrastructure to make the Googles of the world work, to make the Microsofts of the world work, things like that. We also have to have people that are experts on designing statistical algorithms, mathematics, right? Different algorithms that the computer scientists and coders are actually going to implement to detect the patterns in the data. So that's, for example, where someone like me might fall. My primary training is in math and stats, right? You don't have to be an expert in any one of these fields because it's so cross-cutting, right? Everyone is going to have a role to play, and we'll talk a little bit more about that as well. And then lastly, the main big component here is domain knowledge and expertise. So this can be very technical, or it might be something very broad. But at the end of the day, the person whose job it is to provide that domain knowledge, sometimes we refer to them as a SME or a subject matter expert. Their job is to provide context for the problem. All right. So if me, a working data scientist, was to be paired with one of you, a researcher at the NIH, I'm going to have no idea, right, what protein folding is all about. Or I'm not going to have any idea of the nuances of kidney failure or diagnosing diabetes and things like that. I would rely on you to help me with that information. So it's very much a joint effort. And we're trying to share different resources and ways of thinking so that we can uncover these insights together. So the domain knowledge and expertise can't be overlooked because it provides context to otherwise relatively academic fields. That includes math and stats and then the computer science portion. We like to think of data scientists as sort of being this unicorn, this sort of hybrid that lives in the triple intersection of all three of these fields. But again, primarily people aren't experts across all three of these disciplines, right? You can develop that over time, but a lot of times it's much more collaborative. You're not relying on one single person to be your data science expert, to be a master in all three of these domains. Okay, now, as we talked about, the importance of data when it comes to, of course, data science, but more specifically artificial intelligence, cannot be overstated. Data typically, as many of you I'm sure probably know from painful experience, a lot of times your data is not exactly in the format that you'd like it to be in. A lot of times the data is, something you need to aggregate across multiple sources. So it's very, very raw in its original format. And a lot of time is then spent taking that raw information and turning it into something that's a little more organized, turning it into something where, formatting is consistent, particularly if you're taking data across multiple sources, right? Dealing with missing data, for example. Am I going to impute some missing values, meaning replace missing values with a known value, say the mean, if it's a numeric quantity, or am I going to drop missing data, for example, getting it into more of an organized structure so that we can then start extracting those meaningful insights from it, which is what our end goal is as data scientists and as practitioners and users of artificial intelligence. We like to tell people a lot of times they think they have an AI problem. They think they have an issue understanding artificial intelligence, and that certainly is a big piece of the puzzle. But a lot of organizations and a lot of people that are new to working with machine learning and artificial intelligence, I don't think quite understand the gravity of the fact that they likely have a data problem first and foremost, whereas the machine learning and artificial intelligence component comes in a little bit later. And it's also sort of a general rule of thumb that if you're spending about 80% of your time getting your data organized and cleaned and prepared for further analysis for use in a machine learning algorithm, you're likely doing something right. Okay, that is often what's taking the bulk of your time. Okay, so once your data is structured a little bit better and organized, then you can start extracting knowledge from that data, right? Seeing the patterns that exist from it, thinking about ways you could take action, whether that's providing a patient with a certain type of diagnosis, right? Whether that's early detection of some sort of disease that you're interested in finding, right? All of these things are actionable insights that you can gain once the data is a little more cleaned up and ready for further analysis. And you can see the feedback loop, right? Once you make that decision, you're going to gain wisdom from the real world about the value that decision had. Okay. And then a lot of times that is feeding back into, all right, we might need to collect some more data based on the feedback we're getting from the real world decision that we've made. So as promised, here is that relationship between data science, artificial intelligence, machine learning, and deep learning. These, of course, at their core are very technical subjects, right? And depending on how deep you want to go and your understanding is going to dictate just how much time you're going to have to spend on each of these fields. Again, here our goal is to just provide you with a basic overview and understanding. So it'll give you a high level contextual understanding. Again, there are always going to be slight nuances. This is a little bit of an oversimplification, but overall, for the level of conversation we need to have, is perfectly appropriate. So again, we talk about data science. How do we extract meaningful insights from data? That's the goal there. So, and I would like you to think about each time you drill down in this diagram, you're answering the question, how? So, okay, I've got some data and I want to do data science. Well, how do I extract meaningful insights from data? Well, one approach to doing that is to use artificial intelligence. And by artificial intelligence, we simply mean a collection of methods that allow computers to perform at least as good as, if not better, than human beings on important tasks. So a very simple, basic example could be argued something like a calculator. A calculator represents a very basic but important type of artificial intelligence. That system, that computer, is just as good, if not better, than human beings at performing things like arithmetic, even some basic calculus, things like statistics, right? We have calculators now that are very high powered that can often do much better than a human being at that task. Okay, so artificial intelligence in and of itself is just how do we get computers to be good at a particular task? So again, as we drill down, you might say, well, how? How do we go about getting computers to be as good, if not better, than human beings at particular tasks? And a particular approach to that is something called machine learning. So machine learning is essentially letting computers find patterns in data more or less on their own in an automated way. So you're not necessarily instructing the computer. You give it some high-level guidelines as to what it is, the types of patterns you're looking for, and you let the computer do the rest. And we're going to have some analogies in a few slides as to the best way to go about thinking about that. I'm going to spoil it just for you a little bit for you here. It actually helps to think about machine learning as akin to baking in a lot of ways, and we'll see that analogy spelled out a little bit more. But for right now, machine learning at a high level is simply letting the computer look for patterns in the data. Again, that data could be numeric in nature, that data could be image data, that data could be text data, right? All of the above. And then you say, okay, well, how do we get machines to detect patterns in data? There's an approach called deep learning, and that conversation we'll have in just a little bit. It's going to be easier to describe what deep learning is once we have a picture on the screen. But essentially what we're trying to do is model the way that the computer picks up on patterns after the human brain. That is the goal of deep learning. So extracting meaningful insights from data by letting computers look for patterns in data on their own. That is essentially what modern artificial intelligence is all about. Finding patterns in data by letting the computer handle as much of that as possible. That's artificial intelligence, modern artificial intelligence. So we might ask the question, well, why now? So artificial intelligence, this concept and the math and the stats and that kind of stuff has actually been around for quite a while. And you could argue there's different periods that you could argue marks the beginning of artificial intelligence. It is not an exaggeration to say that one could reasonably argue that it dates back to even the 50s and the 60s. So if the history of AI could, conceivably be argued to have started 60 or 70 years ago, why does it feel like there's just so much recently in the news from my boss, right? All these organizations that are saying AI is the way to go. So what's the deal there? Okay, like most things, this is multifaceted. We just want to give you a high level understanding of some of the big components there. So first and foremost, our ability to collect large volumes of data. So it shouldn't be misunderstood. There was a time where storing just a couple megabytes of information took something the size of a refrigerator, right? And now we can store petabytes of information on something the size of a thumbnail. Okay, so our ability to store large volumes of information and do that reliably. There was a time where data was literally stored on like tape, magnetic tape. And so things like the environment, things like rain, things like water, right, corrosion, this can corrupt the data very easily. So one of the big components that can't be overstated is our ability to store large volumes of information in compact ways and have that data persist over time. Okay, that's a huge advent in our technological revolution when it comes to artificial intelligence, because by and large, artificial intelligence systems, the more data they see, provided it's free of bias and things like that, or relatively free of bias, the better. That they're typically going to perform better the more data they see. Not always, but typically. Just a couple stats to give you a sense for just how much data we're collecting these days. So The Economist a few years ago stated in one of their publications that data has actually replaced oil as the world's most valuable resource. You can just think of the amount of data that's generated every day at the NIH, and that's just the NIH, not even thinking about, other, public health institutions across the globe, or other just general data collection and data generating agencies within the US government and beyond, in the private sector, in the academic sector, right? There's just tons of data that's being generated every day. In fact, the most recent stat Eric and I were able to find was from last year. About 400 quintillion bytes of data are created every day. And you'll have to fact check me on this, but 400 quintillion, that is, I think, about 1,000,000 times more than the number of stars there are in the observable universe. All right, so that tells you, and that's happening every day. Every day, that much information is being generated. Now, is the majority of that information useful from an NIH perspective? Of course not, right? We all love the pictures of our cats and our dogs and things like that, but those aren't necessarily the type of data that are going to provide use every day. So obviously filtering out and knowing what's valuable in those 400 quintillion bytes every day is a skill in and of itself. But again, our ability to collect all this, transmit it, is sort of unparalleled, at least relative to where we were, even 50 or 60 years ago. Our ability to process that information also needs to grow, right? So it's great. Okay, we've got all this data that's being stored. Can we actually work with it? Can we actually process it in some way? And it should come as no surprise, I imagine, to most of you here. All right, if you're interested in data science and artificial intelligence, right, you're probably familiar with the fact that our computers are much better now than they used to be. Right, that's essentially the gist of this slide. Okay, in fact, you have much more computing power in your cell phone right now than was had by the astronauts that landed on the moon in the Apollo missions back in 1969. Right. Our ability to do large-scale computations is unparalleled. All right, and the advent of not only CPUs, which is what most people have in their computers, but there are other different types of processing units called GPUs that are what make AI work. If you've heard of a company called NVIDIA, they're in the news a lot. They're one of the main players in making these chips that make artificial intelligence work, which is why they're one of the largest market cap companies in the world, because the advent of AI has really pushed forward the need for what that business produces. Just a little bit more history here. I did my best to include a couple of examples that might be of interest to folks at the NIH. So starting back in 1950, This is where most people would probably argue the ideas for artificial intelligence began with a guy, a mathematician named Alan Turing. He's famous for have broken the Nazis' Enigma code in World War II. A movie was made about him called The Imitation Game with Benedict Cumberbatch, I think it was. And essentially what he did is he defined what the first test was for determining whether a system exhibits intelligence or not. And that was called the Imitation Game. It's also now known as the Turing test in honor of him. And the basic idea is if I'm an interrogator, right? So I have a question that I would like the answer to. So I'm on one side of a wall. And if I write that question down on a piece of paper and say I slide it underneath the door, right? And a response comes back to me, right? On the other side of the door, there's either a computer or a human being. I don't know. The response is slid back under the door to me. And when I read the response, if I cannot determine whether a computer wrote that response or whether a human being wrote that response, that would, according to Turing, that system would pass the Turing test or the imitation game. So meaning it has exhibited some level of intelligence, right? That's the idea behind calling, say, a calculator an artificial intelligence, having artificial intelligence capability. If you write your little math question and slide it under the door, you're not going to know whether what you're getting back is a calculation performed by hand by a human being or performed by, the computer. There are some other components there, but I'm going to skip ahead to the 1970s. So this was an interesting one I learned about as preparing for this talk here. So in the 1970s, an AI system called Mycin was created, and this was actually one of the first AI programs that was used for discovering antibiotic treatments for potential bacterial pathogens. So some of this stuff, right, using artificial intelligence for new antibiotic drugs, right? This is something that is very popular today. It was news to me in preparing for this talk that this actually is almost, 50, almost 60 years old now, believe it or not. Okay. Some other large scale elements in the history of artificial intelligence as related to the healthcare space. So back in 1986, UMass released something called DXplain, which used system inputs to help generate diagnoses for different diseases. So, you essentially type in, symptoms, and then the machine was meant to give you some sort of prediction on what the diagnosis should be. Skipping to 2003, this was a huge advent here, the Human Genome Project. This is a really important one for a myriad of reasons, of course, but among them, just the wealth of data that was created. Again, harkening back to that idea that AI typically is going to be a large consumer of data. And so the undertaking or completion of this project marked a huge moment in the potential for AI in the healthcare and particularly genomics. 2017, so deep learning was used to screen for diseases related to diabetic retinopathy. Again, if you were in our data science fundamentals course, we showed the image of the computer vision model being applied to, a retinal image. So the use of convolutional neural networks, that's what that CNN is here. It's a little small, I know, but this CNN is all about. It's letting computers having a system for letting them look at images and try to identify things that a human being would pick up on. And then in 2020, Google's DeepMind was able to predict a protein's 3D structure from its own amino acid sequence. And so I don't claim to know a ton about the protein folding problem, but I know it is a very, very challenging one and is one that I think would win you a Nobel Prize if you were able to sort all of that out. I had colleagues in grad school that were very interested in the topology, the shape, the structure of protein folding. So just a couple of high-level moments there in the history of AI, and of course, right, there's just so much that can still be done. Now, we're going to talk about some of the exciting things that AI can do, and we've touched on some of those there. We also want to provide you with some of the limitations of data science and artificial intelligence, right? With as much of a push as there is today of everything's got to be AI, everything's got to be machine learning, right? We need to take a step back a little bit and take a breath and say, all right, now there are a lot of great use cases, but we need to do that intelligently, no pun intended, and we need to make sure we're doing that in a responsible way. Okay, artificial intelligence and data science are not a replacement for thinking, for creative thinking. They're not a replacement for human beings. They're meant to be assistants. They're meant to help complement the work that we're doing. They're not be all end all wholesale replacements for, for human beings. So understanding what some of those limitations are is very important. So we'll touch on those briefly here. So first and foremost, among the myths that you might hear, and this is not an exhaustive list, but number one is it's as simple as pushing a button. Okay, it may feel that way, right? The Googles of the world, the Apples of the world, right? They've made our life very convenient, right? Even the amount of artificial intelligence that might be embedded in your car. Some of you might even have self-driving cars, or cars that can park themselves at this point, right? We're getting used to having things be really, really easy and having things be designed for us with a very particular use case in mind. But when we go to try and do that ourselves, we realize it's actually quite difficult. Right. So try not to hold yourself to the standard of, what some of these larger companies are putting out there, right? They've got teams of engineers that have been working on this for literal decades. Okay, so when you're trying to bring data science and artificial intelligence to your organization, to your projects, to your specific work, know that it's going to take some time, and there's not going to be some prepackaged solution. In all likelihood, there's not going to be some prepackaged solution where it's just as simple as pushing a button. Data science, myth number two, data science is going to make analysts obsolete, right? You're still always going to need the people that can interpret the results that are coming out of these models, that are coming out of these systems. So we need people that can see past and understand see past just the numbers, see past just the bar charts and things like that, that appreciate and understand the context, and who also can diagnose when maybe a model is making an erroneous prediction or something going down a path that shouldn't be followed. Okay. Every model in the world, no matter how complicated it is, no matter how much data it looked at, no matter how much money was spent to develop it, no model is a perfect representation of the real world. There isn't one. So every model is going to have its shortcomings. Every model is going to have things that it doesn't get quite right. Okay. Now the margin of error you're willing to accept is up to you. But again, these models and artificial intelligence is not meant to totally take your job. They make mistakes and they need human oversight to make sure that they're still performing the way that they're supposed to. Okay, it's too soon to talk. That's myth number three. Right. So you might say, well, we don't quite have any AI tool. I don't have any AI tools available to me right now on my work desktop or anything like that. So I'll just wait until it's, they're available. Right. There's a lot you can be doing in the meantime, up to and including getting your data organized and cleaned up that could really serve you well once you have some of those capabilities at hand. And then finally, myth number four, everybody needs to learn coding. In fact, I would argue that AI is sort of starting to make coding. It's definitely not obsolete, but the ability to use the system to help you write code has really affected the need for people that we're always going to need people that learn how to code, just like we're always going to need analysts. Don't get me wrong there. But the barrier to entry is now much lower than it's ever been. Right. So you do not have to be a coder to make use of artificial intelligence. Some of the demonstrations we're going to show you here are meant to show you don't need to know how to code at all to get some of the value out of an artificial intelligence system. So as we demystify AI a little bit more, at the very, very core of what's going on, again, it's just looking for patterns in data. And how is it doing that? At a very, very high level, it's doing that using statistics. So this comic is meant to sort of illustrate that point humorously. All right. So most people hear the word statistics, they think it's sort of an ugly thing, it's sort of a scary thing. No one is really interested in the crack in the wall, right? This ugly thing called statistics, or at least some of us are. Maybe some of others are scared away. Most people are scared away. So if we then frame though that crack in the wall, that statistics as machine learning, okay, maybe it sounds a little more appealing, maybe it's a little more artistic and it sounds a little more artsy. But then once you relabel that artificial intelligence, right? Now people are interested in what it is you have to talk about. But again, at the very, very core of what's going on here, statistics and probability are what's driving the results from an artificial intelligence system primarily. So what is AI and what isn't AI? Now, this is all of the slides in this presentation are very dynamic, right? You ask us to prepare you this presentation 6 months from now, heck, maybe even a month from now, we might have very different content for you. So the delineations here are not meant to be, ever long, right? A lot of times things are moving from one column to another, particularly what isn't AI will often float into the what is now AI section. So just know that as we run through this quickly. But what is AI? So today it is interchangeable with the term machine intelligence or machine learning. Okay, the overwhelming majority of artificial intelligence today, as we talked about, relies on something called machine learning, whereby the computer is looking for patterns in the data in a way where it's not told exactly what it should be looking for, right? It figures out the best patterns according to some very general guidelines. We'll have a little bit more discussion on that in a minute. It is not meant to be a substitute for human intelligence. As convenient as it can make your life, again, don't start cutting corners, right? The importance of knowing your field, knowing the strengths and weaknesses of the systems, of the models that you're using is very important. There is not one perfect model out there, and so they are not meant as a substitute. They are not the arbiters of truth, okay? They're meant to be sort of like a smart assistant in a lot of ways. The things that AI is well suited to are going to be problems that require little to no contextual understanding on the part of the machine. Again, the more the machine can just be worried, for lack of a better word, about finding patterns in the data, the better. That is what it's designed to do. But understanding what that data represents and what that means and what the ramifications of taking action based on those findings, all of that, that is not what AI is about. That is still very much a human endeavor. As I mentioned, finding patterns in data, of course, right? Very, very important. That is essentially the main goal of an artificial intelligence solution. Things that AI is not particularly well suited to. So again, basically the opposite of what's on the left-hand side of the screen. So anything that's going to require deep contextual understanding, anything that requires the system to really explain how it found the patterns that it did, right? That's not the way this works. Again, think about the inspector connecting all the dots, right? Like the pattern recognition tool, the AI, sort of come hell or high water, is going to look for these patterns, right? But its ability to explain why it's making the connections it's making, that is an entirely different animal, and that's not something the system is going to be good at. AI systems also struggle with uncertainty. They struggle with evolution, whether that is, evolution of the data that they're meant to represent or just general degradation of the model itself. Okay, these things happen, which is also important to keep humans in the loop, keep humans monitoring these systems. Do not just take everything they're saying at face value. So how is AI used in medical care and biomedical research? So I just want to put together a little, why is this important to me type slide. And again, I am not a researcher at the NIDDK. I've really, I've talked with people in the biomedical sciences and liaised with them for a while, but I am by no means an expert here. But we just wanted to give you a few touch points that hopefully whet your appetite and will give you reason to sort of continue on in your AI and ML journey. So radiology, this is a big one. So looking at images essentially to try and detect things like tumors that a clinician may have missed. Early detection of kidney disease. So maybe I've got a lot of data on a patient, right? And in fact, a lot of times the reason AI is being looked to as a solution is because we have so much data and we have so many patients, right? Help us deal with, right? If it was just one or two patients and we had 1,000 doctors, well then, we could look at that kind of data by hand, right? We've got more providers than we do patients and more providers than we have data. But that's not the real world. The real world is we've got a ton of information. Patients, outmatch, doctors. I don't know what the order of magnitude is, but it's probably 1,000 to 1, at least. Okay, don't quote me on that, but you get what I'm saying, right? There's so many more people that need care than typically are able to provide care. So can we look at these volumes of data, things like their blood tests, things like their medical history, different image scans that they've had, and come up with an early detection mechanism? AI is definitely well suited to do that, provided we have good data and the resources to run the models. Diabetes prediction risk assessment, very similar to the kidney disease stuff, right? Can we essentially look at different risk factors, right? Is there sort of a family history, lifestyle factors that might predict that someone is susceptible to having type 2 diabetes later in life? And then glucose monitoring for things like type 1 diabetes, right? You could have an AI system that models the different blood glucose fluctuations that can help then adjust insulin doses that can help you maintain blood sugar levels. Yes, yes. Thank you, Parker, and thank you, Chris, for asking. Yes, we will definitely. The slides will definitely be made available to you at the end. Absolutely. Okay. Oops. Okay. So as promised, we want to give you a little overview of how machines actually go about learning from data. All right, and we like to do this using an analogy. I'm actually going to drop a link in the chat because I'm going to play around with something, and you can play around with this as well. And again, this is definitely an oversimplification, but it's not such an oversimplification that the main ideas don't apply. Okay, this is a basic view of this, but overall, this is how a lot of the machine learning algorithms that are out there, the things like the Chat GPTs of the world, the things like Microsoft Copilot, this is really how these things work at a high level. So machines learn in a way that's similar to baking in a lot of ways, right? So on the left-hand side, we have data. So data and machine learning, that's akin to baking with your raw ingredients. Your data is your raw ingredients, right? And that's typically going to be human provided. Now, there are definitely systems out there that can produce data, but overall, human beings are providing the data to the systems that we want it to analyze. Next, right? If you're baking something, well, what has to happen next, right? There's lots of things that could be made with flour, sugar, butter, cream, salt, right? There's lots of different things that use those same ingredients. So we have to decide what is it that we want to make with these ingredients. Okay. So the tasty treat is what you want the model to do. I want the model to look at, images of, retinas. I want the system to analyze, this patient data to see if someone's at risk for type 2 diabetes, right? I have some stated goal that I want the model to achieve, right? That's just like selecting what it is you want to actually bake. So you might ask the question, well, if the data is human provided, and if the model output is human provided, well, what is it the computer is doing, right? What the computer is doing in terms of the baking analogy is determining, okay, if what you want is a cake with these ingredients, how much of these ingredients need to be mixed together? Should we be using 10 cups of sugar or 3? Should I be using 50 tablespoons of butter or 4, right? Getting the right combinations for the desired end state, getting that right, that is what the machine is trying to do. And those are what are referred to as model parameters. The adjusting of the mixtures is known as tuning or training a model. And so what I just dropped in the chat is something we can play around with really quickly here to hopefully illustrate this concept. And I'll have a couple others you can play around with on your own. I'll drop some other links in the chat, but we'll do this one together just in the interest of time. Okay, so here what we have is we have 2 raw data points. So our raw data is indicated here by these red dots. Okay, so 0, -2 is the first data point, and 6, 10 is the second data point. Now, a model is going to be governed, it's going to be dictated, its behavior is going to be dictated by a collection of numbers. Those numbers are called parameters, model parameters. Again, you can think of a model parameter as like, you can think of M here is like how many cups of sugar need to be part of this recipe. Okay, and you can think of the second number B, as how many tablespoons of butter need to be put as part of this mixture to get the model to represent the data just right. Okay, and so the idea here is to adjust, right? So right now we're saying, okay, maybe I want to use 1 cup, let's say 1 cup of sugar and 2 tablespoons of butter. Right now, that's not terrible. That's not a terrible model, okay? But certainly we could do better, okay? And this is exactly what the computer does. It goes through a trial and error process. It continually adjusts these numbers until it gets the behavior just right. Okay. So in this case, okay, it's maybe a little hard to interpret through the baking analogy, but we're using 2 cups of sugar and -2 tablespoons of butter. Okay. So the analogy breaks down just a little bit there, but hopefully you find that a little bit insightful. And this is what larger scale models are doing. The ChatGPTs of the world, the Copilots of the world, right? This model only has 2 parameters, but the ChatGPTs of the world, those models have billions or even trillions of these parameters. But the idea is still the same. Go through this trial and error process so that the model, okay, the black line in this case, fits the data as best as possible. I'm going to drop a couple links in the chat for some other things for some other examples you can play around with on your own. If you find this sort of thing insightful. If not, that's okay too. But 2 slightly more complicated examples that you can play around with as homework if you'd like. Okay, so that's what we just did. We fit a linear model there, and we went through the model training process using just a simple 2-parameter model. The quadratic and cubic model you'll see are more complicated. Right, so those are going to have 3 and 4 parameters respectively. By increasing the number of parameters, by increasing the number of numbers you can adjust up and down, that allows for more complexity. So that's why when we're having something like a ChatGPT, we need billions or trillions of parameters, because modeling the way human beings interact and speak with one another, that's a much more complicated problem, and it has a lot more data points than just 2. But again, the principle is the same. And the last component here of the demystifying AI section is what's referred to as deep learning. So you might have heard of this. We mentioned it in the nested diagram image before. This is a very special type of approach to machine learning and artificial intelligence. These are the algorithms that are powering the most powerful things that you're hearing about on the news today. Again, whether that's ChatGPT, Copilot, you might have heard of something called DeepSeek that was put out by a Chinese research team. You may have heard of something called Claude by Anthropic. Right? All of the things that are really generating the headlines in the news, they are driven by these deep neural networks. Okay. Now we're not trying to get anybody to understand these things at a deep level, no pun intended. The takeaway we want you to have here is that they are a huge driver for why AI is so popular today. These types of neural networks, these types of AIs were created in 2017/2018. So they're relatively new, and that's why we're seeing a lot of the breakthroughs that we're seeing today. So they're relatively new. And the other thing that's important to know about them is that they follow in the footsteps of an engineering principle known as biomimicry. Biomimicry is where we have a real world challenge, an engineering challenge that we're faced with, and we look to nature to try and help us address that problem. So you can think of, if I'm trying to design an aircraft that is very aerodynamic, I might look at a bird of prey, I might look at a hawk, or I might look at a falcon or something like that and design my aircraft to replicate that sort of design. As humbly as a member of the human race can make this claim, right? If your engineering problem is to detect patterns in data, you'd ask the question then, what is the best thing in nature that we know of that is great at picking up on patterns in data? And again, as humbly as a member of the human race can say this, it's the human brain, as far as we know, right? And so these deep learning neural networks are designed, the math and the computer science, the way they're programmed, is meant to replicate the way the human brain picks up on patterns. And that's what this image is meant to indicate here. Okay, if you want to ask more detailed, nuanced questions, we can talk about that at the end. But hopefully you can sort of see the sort of what the image is driving at, right? You've got this collection of nodes, right, that are sort of akin to neurons in your brain. These nodes are all connected together essentially, and they share information between one another, right? And that's how your brain works at a high level, and that's essentially how these deep learning neural networks work. And these have proven to be extremely useful circa 2018 and beyond. Okay. So I think this might be a good, I know we got a tight time schedule, but I think this might be good. I know I've thrown a lot at you. Let's take a quick, let's say like let's say 3-minute break. Let's say 5 minutes. We'll do 5 minutes. I'll put up a timer, and I want to make sure if there are any questions, I get to those as well, because I know I'm throwing a lot at you. But let's take a quick 5, and I'll stick around for any questions that you might have to this point. Like I said, I'll put up a timer here so we can all stay on track. Now it's best to, usually people have about an hour, an hour of attention, and then they need a little pick me up or something. So. Like I said, if you do have a question, feel free to come off mute and let me know.
I had a quick question if you're not taking a break yourself, but just
No,
to squeeze it in.
Please.
So I'm a traditionally trained statistician in the sense that I have a PhD in plant biology, and so I learned kind of I guess traditional biostatistics. And I think what I find the most confusing about certain types of AI models or machine learning is like, is this Bayesian statistics that I'm familiar with, just like in a trench coat, or is this because I think what confuses me is it seems like there are not as many quantitative measures of uncertainty or quantitative outputs by which a model or a machine learning algorithm can say, like, here's how sure I am, or here's the amount of variation. I don't know. I just like, do you feel like in the AI community, there has been a lot of interest in designing measures of uncertainty, or like they're kind of taking that problem seriously, or am I kind of misunderstanding entirely?
No, it's a fantastic question, and assuming I'm understanding, exactly what you're driving at. So there are definitely like Bayesian statistical like neural networks that have been designed that I've seen. Those are not, from what I know, right? These models are, especially the popular ones in the news and things like that. They are, to my knowledge, not relying on a Bayesian approach to statistical methods. A lot of what they're doing is using what's called it's called the softmax exponential function to decide what the probabilities of something are. From an abstract point of view, any function that sort of integrates out is increasing and integrates out to one can serve as a probability distribution. So that's what this softmax thing is. Am I answering your question? The short answer is they're not always using.
Yeah, that does help. I mean, mostly it gives me things I just need to Google more after. But no, that is helpful. Thank you.
Yeah, and the design and the thought that goes, like, this is what's so cool about this field, for me, and it sounds like for you as well, right? There's so many assumptions as to what types of functions and what approach to probability and statistics you're looking at that would influence the way these things behave. But to the best of my knowledge, that's not what some of the most popular algorithms are relying on.
Awesome. Thank you.
So a question from Michael in the chat: given that many university funded research projects hire statisticians or biostat students as research assistants, Will AI replace them since many of their jobs involve fairly routine methods? Yeah, so I wish I had a crystal ball there. What I have seen over the last, whatever, 4 or 5 years of working in this field is that it seems to be people who are not taking the time to upskill and learn a little bit about how AI can improve efficiency, can improve their decision-making capabilities. That's where we're seeing a lot of the disruption, at least right now, is not embracing at least components of it. We're not seeing necessarily outright replacing. I mean, it's definitely happening. I'm not saying it's not happening, but the overwhelming majority of the shift seems to be more in people who are dug in and they're just not like wanting to learn anything new at all and getting passed by people that are having tools and skills available to them that allow them to work much quicker and to your point, automate out or expedite some of the more routine stuff. Yeah, so it's a good question. Hopefully I've answered your question there, Michael. But it's an exciting but also scary time, because who knows exactly how the cookie's going to crumble. Okay. Yeah, so thank you very much for the questions. That's why we love doing these live discussions, right? We want to have the opportunity to answer your questions in real time. So we'll spend a little time here. Primarily, this section is meant to be, I'm going to provide you a collection of references. Responsible AI use is very important, of course. A lot of this is going to come down to, data security and data privacy considerations. It's not, that's not the be all end all, but a lot of that is what responsible AI use comes down to. All right, so I put together a collection of documents and resources that you can, I want you to look through as you have the time. There's definitely a wealth of biomedical data out there, and AI opportunities are, of course, present to different research communities that are trying to make this data as findable, accessible, interoperable, and reusable, or what the NIH is calling as fair as possible. This ODSS, this is the Office of Data Science Strategy. I'm going to drop a link in the chat for you there. If you haven't taken a look at their website, I highly encourage you to. There's a lot of changes happening right now with regard to different policies across different organizations, and AI is just as susceptible to that as any other sort of initiative. And so it's good to stay current on those things, especially as we move into a new era of different priorities and things like that. But from what I found in researching for this talk, the use of artificial intelligence in fair, ethical, and in ways that are reducing bias to the greatest degree possible, trying to control for health disparities, is still a priority of the NIH. So highly encourage you to look into that as well. Bridge to AI. So this is another really interesting one. I'll drop a link in the chat to this one as well. So Bridge to AI, this is about bringing technological and biomedical experts together with social scientists and humanists that is trying to make AI solutions as equitable as possible, particularly in the biomedical space. Excuse me. And then lastly, advancing health research through multimodal AI. So when we say multimodal AI, we mean artificial intelligence solutions that have a number of capabilities. So that could include things like chat features, that could include things like a generative AI in terms of creating images, analyzing images, looking at video, powering robotics. That's what we mean when we say multimodal AI. They're capable of a variety of different tasks. This is something that ODSS, again, that's the Office of Data Science Strategy, is highly invested in. And there's documentation at that third link provided if you're interested in learning more about the different opportunities, risks, and challenges that are associated with the use of multimodal AI in the NIH. Some policy guidelines that I put together for you here as well. So again, I'll drop the link in the chat to the source that I'm taking this from. 1 second there. Okay, so the NIH's AI policy, from what I could suss out, rests primarily on 5 pillars here. So there's research participant protections. Okay, so 45 CFR 46 is outlining the basic provisions for institutional review boards, informed consent, and assurance of compliance for NIH-supported research that involves human participants and their data. As I mentioned, right, a lot of this stuff is going to be around data privacy and data quality. Okay, Next, we've got data management and sharing. So this is establishing the requirement to submit a DMS plan, a data management strategy plan, and comply with NIH approved plans, right? Anytime you're working with PHI or PII, public, personally identifiable information or personal health information, right? The types of hoops that you have to jump through are, long but important standards for making sure people's information is protected. When it comes to peer review, so artificial intelligence technologies and their outputs are not immune to needing peer review. So if there are results and things like that that were obtained through the use of generative AI, things like large language models, for example, things like tools that are analyzing your data, peer review is still an extremely important part of verifying results from research. Biosecurity and biosafety. So this is research funded by the NIH, includes using the research tools and technologies that are enabled or informed by AI are going to fall under this oversight framework. This was actually the one that was kind of the longest and most detailed, so it was hard to kind of summarize all the things that were listed out in biosecurity and biosafety. But if you follow that link that I dropped in the chat, the most recent one, you can read more about that there. And then, of course, right, we touched on it a little bit, but health information privacy. So HIPAA considerations are extremely important when we're talking about PHI, making sure, right, you're never uploading sensitive information to a third-party app. So whether that is, OpenAI's tool or any other, right, you're never putting sensitive information up there, right? You're only using systems that are approved for that level of information. Now, you might not have access to something like that quite yet, but again, in the last few years, I've definitely seen lots of progress made. And I'm going to demonstrate some tools here that have been made available to me recently that hopefully, if you don't have Copilot yet, something like that will be approved, because it really does make your life a lot easier when it comes to data analysis and working with documents in your SharePoint page and things like that. Okay. Again, we will share the slides with you here. I dropped some important links on NIH AI policy in the chat, but we put together a more exhaustive, comprehensive list here in the notes for you as well. I'm not going to click through these. Again, lots of reading to be done there, but we wanted to make sure that you had a one-stop shop when it came to the notes of some of the most important, policy guidelines and links for finding that kind of stuff. So you will definitely get this as soon as I send the slides out at the end. Okay, so last couple of things we want to talk about here before we jump into the demonstrations are what sort of roughly the AI lifecycle looks like. And again, all of this can be broken down into like real minutia. Feel free to look at the finer points in the slides here. But overall, most data science and artificial intelligence projects are going to follow 3 to 4 general phases. Okay, so there's going to be a planning phase. There's going to be a phase where you need to define what your problem is, what type of data you have access to, right? What you want to do with that data, and then determine whether AI or data science might be the right approach for that problem. If it is, try and select the right tool for the job. So planning, fairly self-explanatory. Okay, there are a number of questions you might want to ask yourself during this phase, including things like, has someone else tried to solve this problem before, something similar? Can I leverage their approach? What does success look like? What does it mean to define error tolerances, right? Again, no model is perfect. So when they start making mistakes, once you start picking up on those, how much slack do you have there, right? You have to define what those success metrics look like. Next is development. So, okay, we've decided we want to take the next step, right? Maybe we want to develop some type of solution here. A lot of times what this is going to look like is we need to start cleaning up our data. We need to get our data organized so that it's prepared for the models themselves, right? We also may develop multiple models. There's not just one approach that's going to work. A lot of times your first approach is not going to be the one that ultimately is, the thing that you're using, in the future. A lot of times your first approach is meant to serve as a baseline so that you have a point of comparison as you try more complicated, more detailed approaches. Right? So this development phase is sort of experimenting around, seeing what's out there and testing out different approaches from a modeling point of view. Okay. So some of the questions you're asking here is, right, what type of model bias could be out there? Who owns the system that it is I'm trying to use? A lot of AI systems are now too complicated. You're not going to be able to just run it on your laptop. right? So how do I connect with different resources? Where am I getting the data from? How do I maintain this thing once I've stood it up? Those types of questions are very important. Right. And then finally, there's going to be a deployment phase. So, right, we've tested this thing out, right? It seems to be working. I seem to be getting results that are making accurate diagnoses, right? It's even maybe doing so better than, you know, a radiologist or a human counterpart, right? Now I want to get this thing out into the hands of the masses. How do we go about doing that? And that, of course, takes a lot of work and orchestration, requires a lot of times people with IT backgrounds and skill sets that go far beyond just working with data and modeling. But a lot of times you're trying to get what it is you've built out to some wider audience that's going to use this solution to drive real change. Okay. So is there some type of process that's going to be in place once I deploy this thing out so that we can monitor how this behaves? It's very important to understand, as we've talked about, artificial intelligence, it relies on machine learning, which means this system is continuously learning from new data that's been introduced to it. It's continuously updating itself, right? It's not a static product that we're creating. And so as the data evolves over time, as the way that people interact with the system evolves over time, its behavior is going to inherently change. And sometimes that's for the better, and sometimes and a lot of times that's for the worse, right? Things will degrade over time. And so even if you released something that was working perfectly and was, you know, this shining example of how AI should be used, if you fail to monitor it, if you fail to, you know, keep an eye on the types of data that it's introduced to, it can very quickly and very easily degrade over time if you're not staying vigilant on that front. So monitoring the way these things perform over time, because they will evolve on their own, is extremely important. Okay. So I'm going to skip this demo for now. There's some other demos I want to get to. Again, it's just an interest of time kind of thing. I'd rather have too much content than others, but if I have more time, I'll come back to that one. But I want to make sure we have time at the end for a couple more, what I think are relevant demonstrations. So AI operations. So here, there are three main components. So we're talking about trying to do this design, develop, deploy aspect when we're coming up with AI solutions. So there are three main components that go into that. So there are data ops. Okay, data ops is all about getting your data organized, understanding how it's structured, storing it in the right types of frameworks. So going back to the ingredient analogy, data ops is not all about, but a big part of it is making sure your data is stored the right way. So just like if you go to the grocery store and buy, you know, a gallon of milk and a canned item, right? The gallon of milk should be stored typically in the refrigerator, and the canned good is going to go in the pantry. Similarly, data should be stored in appropriate storage mechanisms. So some types of data are going to be stored in something as simple as an Excel spreadsheet. Other data are going to be stored in, you know, relational databases using tables and things like that. Other data, like images and things like that, are going to be stored in different types of databases. So having an understanding of what type of data you're working with is going to dictate the way it's stored. ML ops is all about looking for those patterns in the data, letting the computer find what those patterns are, testing and overseeing how the model is performing over time, evaluating it constantly against the metrics that you have defined for success. And then finally, DevSecOps, we talked about deployment, right? So how do we get something out into our end users' hands? Your DevSecOps teams are the ones that are typically responsible for scaling something up, making sure that the data is secure, making sure that the code is written in an efficient way so things run smoothly and properly, things like that. So as you can see, it definitely takes a team effort when we're talking about artificial intelligence at an enterprise level. Okay. Now these fields are interconnected, of course, right? ML ops is all about training models, right? That relies on data, of course. So your ML ops folks are going to be connected intimately with your data ops team, even if they're not the ones that are necessarily managing the data on a day-to-day basis. Similarly, your DevSecOps teams are going to be the ones that are concerned with orchestrating and getting this thing deployed out on a larger scale. So they're going to be liaising with the data ops and ML ops teams to make sure they understand exactly what the model requirements are, exactly where the data is stored, and how to best provide access at a large scale to the things that the data ops and the ML ops team have created. Data governance priorities. So this is what we touched on a moment ago, right? So I won't belabor that too much here, right? It's very important to know where your data is coming from. It's very important to know what types of models are being used, know what types of strengths and weaknesses they have, particularly models and data that are coming from protected information, whether that's HIPAA regulations, whether that is FedRAMP and FISMA. These are regulations that are placed on members of the DoD whenever they're trying to stand up cloud computing resources that are going to handle sensitive information. Okay. We talked about machine learning ops there. So machine learning ops, again, this is just the component of the AI ops process where we're interested in training and letting the models learn from our data sets. There's typically a machine learning lifecycle that includes developing, vetting, and model operations. Development is all about choosing the right model, choosing the right data to work with. Vetting is the overseeing of how this thing evolves over time. Again, the system will learn from new data as it's being introduced to it in real time. And so continually monitoring that, making sure it's doing what we want to do, staying vigilant is extremely important. Okay. And then as discussed, DevSecOps, this is all about the large scale orchestration, including making sure your solutions are locked down against attack. Because again, these systems, AI systems, are looking for patterns in the data. So if someone is injecting bad information or biased data into your data set, something we refer to as poisoning, okay, the machine isn't going to be smart enough to know what's good and what's bad data. It's just going to make those connections. It's going to detect those patterns no matter what. And so if someone has access to your data or to your model and can affect the way it's behaving in that way, the pattern recognition, behavior, that's a problem. And so DevSecOps is extremely important for layering on that security, making sure people can't access what it is you've developed. Okay. Okay, so I see we're coming up a little bit tight on time here. So just some slides here on the different components that go into, right? So this is just meant to sort of holistically describe the relationship between your data ops folks here on the left, your data engineering, analytics frameworks, or your ML ops people, and your digital architecture, your DevSecOps folks, how they are trying to work together to combine their technical components with the responsible AI components to provide an AI capability that is robust, again against attack, and providing value to your organization. With regards to AI solutions, there are three main components that go into creating an AI solution. So those are designing, developing, and deploying a solution, which is what we touched on just a moment ago. Right. Now, there are different process models out there for describing what some of those requirements are. Okay. In the design phase, that includes things like identifying and formulating a problem, figuring out what ethical considerations you need to consider when working with your data, exploring your data, and maybe acquiring some data from an external source. This is all going into the design component of your solution. When it comes to developing a solution, right? Again, this is where your ML ops team comes in. Okay. A lot of times they're going to build out some initial model like we discussed earlier. They're going to evaluate how that model performs against a benchmark for success. Any sort of shortcomings are then typically going to be supplemented with an alternate model, something that's going to buttress the weaknesses of the initial model that was built out. And then attempts to try and explain why the model's doing what it's doing. Typically that's easier said than done. But a lot of times we're putting an investment in understanding the way the model actually performs. Okay, and deployment, again, at the end of the day, we want to get this thing in some user base's hands. And so here, right, how do we rely on our DevSecOps team to get this thing deployed? How do we then review the way this thing is performing in a realistic framework, in a realistic setting, and then continuously monitor this system for performance degradation over time, which is essentially guaranteed if you're not paying attention to the way the data is being presented to the model. Now, there are three components that go into driving this design, develop, and deploy. Obviously, there are going to be people at the core of your workforce. Okay, a lot of times these people have both technical and non-technical skills. We have people at the leadership level that understand what the mission is, what the need for this product is. We have people that have a domain business or expertise that are going to be able to interpret the results of what is being analyzed. The middle components, we've got data engineers, data scientists, machine learning engineers, and software developers. Again, these are our AI ops folks that work in data ops, ML ops, and DevSecOps, like we touched on before. And then lastly, it's worth stating the importance of reporting out your findings. So people that can visualize and create things like dashboards, compelling narratives around what it is that you've discovered. Processes. This is all about how we go about working with AI systems. What are the rules that are in place? So we talked about the AI rules that are in place at the NIH, right? What are the rules and the guidance that are put in place, right? The DoD, for example, has their own set of guidelines and regulations. It's important to stay current on those things because they're going to dictate exactly what type of data you're allowed to work with, exactly the way that systems are accessed, right? The types of rules around, data sensitivity and data privacy, as well as how these models are put into the hands of the people, as it were. And then finally, there's the technological component, the fun component, as it were, right? So what is it that we're using to actually drive some solution forward, right? There's lots of different platforms out there, including things like AWS is Amazon Web Services, Microsoft's Azure, Google Cloud. There are all kinds of different databases, ways of storing the data. There are ways of accessing the data through things like SQL commands or maybe through a programming language like Python. There are different data analysis tools, data visualization tools. The list is sort of endless in terms of what capabilities are out there, depending on the data that you're working with, depending on the capability that you're interested in doing. Right. And what I'd like to leave you with here in the last minute or two is just an example of how we can use tech to make our lives a little bit easier using something like a Microsoft Copilot. So I'm not sure if this has quite made its way onto NIH machines or not yet. If it hasn't, I would bet it's not too long, too far out into the future. If you run Windows at home, in all likelihood, if you've kept updated with system updates, this is already something that you have available to you. What I'd like to demonstrate is just a simple capability using SharePoint that I think will have some real value. So Microsoft has a partnership with OpenAI. They've given billions, literally billions of dollars to OpenAI to create what is called the Microsoft Copilot application. And Copilot is essentially an assistant that is embedded now into almost every Microsoft application, including SharePoint, including Teams, including Excel and Word and all that kind of stuff. And so what I'm going to demonstrate for you here is the use of what's called an AI agent, And so it's as simple, okay? It's as simple as having a folder on your team SharePoint page. And so you see I created a folder for today's demonstration that I upload a handful of documents to, right? So just to give you a sense for what it is we're looking at in this folder. Okay, so I have a document on some statistics about diabetes mellitus, DM, okay, from 2015. Okay, so this is a document I pulled from PubMed that's included in this repository, my SharePoint. I also have a document on chronic kidney disease that's in there in PDF format. And essentially what the technology will allow me to do is talk to this data, talk to these documents using a chatbot feature. Okay. Now creating an AI agent is as simple in your SharePoint page once you've got your documents uploaded as clicking new and then agent. So it will literally create this agent that allows you to interact with your documents. And once the agent is created, you can make queries on the data in your SharePoint page, right? Now, it doesn't have to be just text data. That's what we're working with here. But just to show you here, right, one of the things that I can ask it about, do one quick example here. Where did it go? So we had, oh, sorry, guys. We had this document here. So this research paper outlines strategies used to reduce the progress of chronic kidney disease. And I can ask, because this document is part of my SharePoint page, it's part of my agent's knowledge base, I can ask it what are these things, right? So if I didn't have time to read through this whole document and find that, I can ask my agent here on the right, let me just make sure I get the prompt exactly right here. So I had some of this stuff typed out here, just in the interest of time. Okay, so what are some strategies to reduce the progression of chronic kidney disease? And because this agent is able to pull information from the documents that I've uploaded to the SharePoint page, it's going to know, right, what those things are. And you can see here, medication, blood pressure control, and that's all mirroring exactly what you're seeing here, right? Blood pressure control, controlling hemoglobin levels, things like that. Okay. And the other great thing about Copilot is it provides you a source for that information. So it's saying, I'm pulling these numbers, this information from the PDF called chronic kidney disease. That's where I'm getting this information. So you can always fact check what Copilot is coming up with. So I know it's a little bit quick. I'm more than happy to stay on the line for any questions or any further demonstrations of the technology, but I wanted to make sure we at least saw one really cool application of Copilot and using it in your SharePoint page. I definitely want to open it up for any questions there might be, and I also want to thank people for the time. I know it's tough to carve out an hour and a half out of your day, especially in the middle of the week like a Thursday. But with that, I'll hand it back off to Ms. Cooper.
Thank you. Thank you so much. Thank you, everybody who attended today. We do have a quick poll up here, if everybody wouldn't mind filling this out before you leave. And I hope to see you again next month. Thank you so much, Dr. Ayala.
Thank you.